If you can ping Jack also,
Oh yeah.
maybe you guys have some medium in which you communicate and see if he wants to join. That we need to wait for him, but just to
No, yeah, we'll ping him.
go.
Cool. Should we wait a little bit for Jack or get started? What do you think?
I think we can start and then we'll take things as they go.
Okay, is anyone dying to go first? I think, oh, by the way, maybe I should say first, curious what you think about the format. I was just thinking we just go around, everyone who like looked at some problems can just talk about them and share their screen and, explain what things they did. And then also feel free to bring up projects that you're working on that you would love comment on or something. Well, okay, that's self-serving. I know, Martin, you mentioned something like that, and then I was like, oh, I totally have things that I want to talk about too. Please, let me use this form. So how does that sound for everyone? Is that okay?
I think that's a good format.
Yeah.
I mean, I know that my walkthroughs through the solution, the exercise that I chose is going to be like 5 minutes long. So I think there'll be time today to discuss some other things.
Cool.
Yeah, mine are pretty simple too.
All right. So who wants to start?
Carl.
I knew it. How did I know? Why? What? Okay, so I'm going to start off because I'm going to set the bar real low. Like, I am really going to lowball that one, because everyone who's getting recorded here just needs to, like, feel very comfortable. And so I'm going to embarrass myself, which is I'm really excited for. I've been looking forward to this moment for a long time. So let me share my screen with my awesome proof that I wrote 2 minutes ago. So I ran out of paper, actually. So this is my notepad. I wrote on the back of a notepad that I, ran out of. So first, actually, before I show you a bunch of crap, let me open up the textbook and read the problem. So make this bigger if I can. So the war of attrition. It's a very brutal game theory concept. So essentially, it's two players. They both have they want to outlast each other, essentially. The concept is the key thing about this problem is that every unit of time, they lose some kind of unit of utility. And they lose it at the same rate in this simplified version. And so what that means is you start out with this high value that you're going to get as a reward from outlasting from one person. Oh yeah, you have two choices. You can either at every unit time you can either you can choose to keep going or secede. So you start out. You have two people. One person has 5 units of utility that they want that they would get from the other person seceding, and the other one has 4 units of utility for the other person seceding. And so as time goes on, you just go okay, 5 and 4, and then one time period goes by. Okay, now 4 and 3, and one another, 2, and eventually you get to the point where someone has negative utility, and by then they'd be very irrational not to have seceded. So this is the general concept. Does that make sense? Cool. So here is the exercise that I underwent, which is formulated as a strategic game and showed that in all Nash equilibria, one of the players concedes immediately. So this is actually a cool property of this formulation of this problem. This problem has many formulations. So you can if you look it up online, you'll see different people explaining it with, different variants of this game. But first I'll quickly go over just I guess I'll go over the kind of plain English rationale for the Nash equilibrium. And I wrote it out without just the cases, but now I just kept the cases for some reason and I didn't write the answers, but I'll explain the answers. So you have 3 cases in terms of each player can have any value that they ascribe to the other player seceding, right? So you get to the point, and this is a 2-person game. You get to the point where you have 3 cases, where either player one has more value, gets more value than has more value. I don't know if value is the right word, but whatever. More value than player
Utility, right?
utility. That is the better word. So, oh man, I did 1 and 0. Should have done 1 and 2. That was my bad. So player 1 has more utility than player 0, or player 1 has less utility than player 0, or player 1, they have equal utility. So these are like the 3 important cases. And the reason why is because a rational player playing this game is able to see the other player's utility in this like strategic game setting. And they can say, okay, so if I have more utility, if player 1 has more utility than player 0, then player 1 will, and player 0 will succeed on the first shot. And the reason why that's the case is because if they were to play it out and they both were losing utility, it would just end up with the actual like time would be wasted essentially, right? You get more utility from leaving immediately, and if you know you're going to lose in the end.
So I don't know if I'm completely following how their utility function looks.
Yes, that is a good question. Continue, sorry.
So, I mean, they start out with a utility, and the longer they both not succeed, their utility drops. But if the other person succeeds, they get utility, or do they just like get to keep what they have saved? Like, can you go over that again?
Okay. Say that again.
Like you say that they begin with like 5 and 4, and so if they both succeed, I mean they can't both succeed, but if they would they get that utility automatically, or is it like once the other person succeeds that the utility is released to you?
Yes, and this is not an iterative game, I believe. I think iterative games are a thing that we will cover in the future. So really the right way to think about this speaking would be like you have the choice to like you would map it out, all of the different at least this is my understanding. I could totally be wrong about this. Like your set of actions include waiting 1 turn and then succeeding, and waiting 2 turns and then succeeding, and waiting 3 turns and then succeeding, right? And so my like the kind of just the rationale that I was giving just now, and I realized that I hadn't covered an edge case, which explaining it made me realize, but if you imagine 2 players, right, they can either choose to, they know how much utility the other player has. If they have less utility than that player, they know that player is going to outlast them. And so it's in their interest to not waste time and just lower the other person's utility, her utility, and just succeed immediately. The thing that I actually didn't consider is I didn't actually, I guess, look at closely enough the utility function because I'm unsure as to whether it would be the same if you would, I believe that you would get less utility if like what utility does the seceder get? That's the thing I'm missing is like what is their utility function? Because if it doesn't matter to them and they get 0 the whole time, it doesn't matter when they succeed. So they have to lose, like they have to gain some utility for succeeding early, which I think they do in this English, but I'm bad at like thinking and reading English at the same time.
Can we have a look at the formulation in the book? If it's clear.
I mean, the formulation in the book, I believe, is this example. But is there another section where they have the thing written out in mathematical terms? Because that's something that I like tried to do, but wasn't able to do very well.
I don't know. I didn't have a very close look at it, but
Yeah, I don't.
I was just wondering if it would be simpler.
Yeah, I can like open this game theory. Oh man, like duplicate it. Yeah, no, I don't. I don't know what that was. Some terrible search right there. Let's see. So I'm gonna assume a formulation, and I can actually write. You can actually write on this, which is pretty cool. So that's pretty cool. Let me see, where is so the value of, should I like, okay, so if we assume, okay, let me just, I'm just going to say it out loud. If we assume that the utility, if you secede, is something higher than your, if the utility that, if you secede early, that you gain some utility rather than seceding late, then just knowing that the other person has higher utility, you are influenced to secede early. Does that make sense? So here, or player. Did that make sense, by the way? So player 2 wins in this case. Oh God, it's not player 2. Jesus. Player 2 secedes in this case. Player 1 secedes in this case. And I believe they both secede at the same time in this case.
You guys definitely made concede.
Concede. Whoops.
Nobody's conceding.
What is
When you formally separate.
that is, thank you for that.
Carl, do you have the number of the exercise in the book?
Yes, I do. It is right here. 18.4.
I don't see a number, but I heard you. Okay.
Oh, you don't see the PDF?
No, we only see.
Oh, really?
Yeah.
Oh,
So
the whole time.
You've been reading a PDF.
Oh my gosh, I've been reading a PDF. That's why you guys are. Oh my. Jeez.
Yeah, we can only see the stuff you were just drawing, although it disappeared.
How about now?
Yeah. Oh yeah.
You see the PDF?
Oh yeah.
Oh yeah, there it is.
Oh, that's why. I was like, I'm reading this PDF. I'm like, oh, it must be here somewhere. Oh,
Yeah. I didn't know what was going on.
damn it. 2 players. Continues round.
So everybody loses 1 unit of payoff. So like everybody starts at 0 utility, and as time goes by, they lose 1 utility point per unit of time, and the last person standing, their utility function will be VI minus T, where T is the time that has passed until everybody else conceded, I guess.
Yeah.
But we're only doing this with 2 players, so yeah. Then it's. I mean, they do receive a reward for conceding because they don't have to lose more time.
Yeah, and the winner, the conceding person, the person who concedes, what is the difference between conceding and the other person? The person who concedes doesn't lose. Okay, so it's negative. So they start at like 0, 0, and then they go negative until the point of concession is reached, and then it adds their value to it.
Yes.
Right? And so that's kind of, to some extent, what I had here. So I just like wrote out, this is a Nash Equilibrium, has my nice handwriting. Just like definition of a strategic game, according to the book. And then War of Attrition, I wrote this poorly formulated function.
But I mean, that is only in the case where they don't concede first.
Yeah.
So in the other case, it would just be minus t.
Yeah. So and now this, I can explain these cases really easily, because you have a position where they both start at 0, but this guy knows that this guy will get more value from staying longer than him, right? So he already knows, okay, it's in my best interest to concede. And then similarly, just like the reverse, this guy knows that. And then if they're equal, they know that every unit of time that passes that they haven't conceded is just wasted utility. And so they both concede at the same time. So does that make sense now?
Yeah.
Okay, cool. Damn, I'm so mad that, oh well. Learning curve, remember to share your whole screen, not the browser window. Anyway, so one thing that I want to do, though, that I could have done better, especially, is like when they say formulate as a strategic game, do they mean essentially writing out, like, you know, these are the set of players, like these are the set of the players' actions, and then like hopefully you guys have done that, so we can kind of see what a good non just hand wavy approach to finding the solution is. So.
I didn't do that. I'm going to be waving my hands.
Okay.
Yeah, me too. But I mean, I guess if you were to do it rigorously, you would say what AI is. You would say, like, AI means conceding. Well, I mean, I would like have AI as the action where you concede after 0 rounds, after 1 unit of time,
yeah,
and so on. So each player has a real number that they can choose from, where the real number corresponds to the time. And then you would map the reference relation as a function over that. I mean, as a function over the Cartesian product over all of the players' actions, which, you know, would make things a bit more formally rigorous than what might be needed. But I guess that's sort of what you would do if you actually wanted to define all of those sets.
Yeah, and I just think that would be useful for like later on being able to formulate this and like write it out and, you know, reason about it and like code, for instance, and like, you know, generalize these things. So
Most stuff.
cool. I guess maybe let's do another person go and share their problem, and then we can all just freeform present what we're working on or any things that we want to question for the group.
Yeah, for sure. So I can go next, but I would like to know how you did that drawing on the screen, Carl.
Everyone can do it. So if you share your screen, I will show everyone how to draw, and we can all have fun.
Is it whiteboard? Am I doing it now? Can you all see this?
Yeah.
Oh, well, yeah, that's one way.
That was easy.
Wait, how do you get a whiteboard?
It was one of the options that you could choose.
Oh, cool.
Clear my drawing. No, you guys, you're not supposed to draw on it.
Hey, we can draw.
How are you drawing, guys, actually?
I think
Oh, it's
they're
in
just
options. Wait.
Okay. Anyway, this is a lot of fun. Okay, so my problem was the second prize auction. And so that is an auction where, wow, this is going to be fun. There is an item at sale, and it is valued by player I at VI. player I values. You can all understand what I mean, but anyway, I'll just write it like this. And so the highest bidder wins the item, but they only have to pay what the second highest bidder bidded. So the payoff for the winner is their valuation. Yeah, let's see. Let's assume that if player I wins, then their payoff would be VI minus. Oh, let's erase that. Okay, holy smokes, this is hard. Minus BJ, where BJ was the bet of the second highest bidder. And so to calculate what the best strategy is, we can, again, form an integral here. Jack, did you write this?
Yeah, I did. You're welcome.
Thank you. This means Martin is very good at explaining in Swedish.
It means dick.
So, like, if we calculate what the payoff for player I is, it's going to be this. Let's just assume that we have two players. In the case of more players, then whenever I talk about the second player, you can just exchange that for the highest bidder among the other participants. But anyway, the payoff for player I is going to be an integral from all of the values where player one bids the highest. So this is an integral that goes from 0 to bi, and the variable is bj. So we consider the bid of player j, and whenever that's lower than the bid of player I wins, and they therefore receive the payoff of VI minus BJ. And there will also be a second term, which is in all of the cases where they lose. So that's VI to whatever, can be infinite here even. And the payoff there is just going to be 0 because they don't have to pay anything because they're not winning the auction and they're not receiving the item. So this is also going to be over BJ. Let's call this P for payoff. And let's calculate what it is in a similar fashion to the first price auction. This is a fairly straightforward integral where we just put BJ in here by BI, and then for the second term we get, can I just not erase that? Okay, good. We get, damn it, screwed up again. Anyway, it's going to be BJ squared, that's a 2, and divided by 2. Exactly. So that's a 0 and 2bi. Okay. And that is going to be bi. Well, we're just going to replace everything here with bi instead. So I'm not even going to write it out. And then to maximize our payoff, we're going to derive this expression with respect to BI, because we want to know which bid gives us the highest payoff. And that's going to be an extreme of the function. And so when we derive this expression with respect to BI, we get, let me abuse syntax a little bit and just write an implication here, even though it's not an implication. But I'll just say we'll get, I'm making this triple arrow, which means we get. Damn it, it's not supposed to be that. Okay, we get BI. The BI just disappears. Minus, and then we just get BJ back here. Okay, and we want to see when that is equal to 0. And now it becomes quite clear that the extreme point of this payoff function is where our, this is an I, yeah, where the bet is equal to the valuation. So it's exactly the same method as in the first price auction. It's just that there's a different Nash equilibrium. Cool. Questions?
Pretty cool.
Yeah, cool. Then you all know what to do if you ever participate in an auction. Bid your valuation if it's a second price auction and half of your valuation if it's a first price auction.
Cool.
Yeah, Martin out.
Who wants to go next?
I think according to the, I think you are the only one who had another.
Okay. Are you on a party right now, Carlos?
No, no, this is the consensus office. Maybe that is a party. I'm just kidding.
Oh, okay. I thought he was drinking something. I was like, damn.
Unfortunately, water. Actually, fortunately, it's the consensus office.
Depends on,
Depends. Okay, it depends on context. Didn't mean
utility functions and stuff.
Exactly.
Okay, I'll go next. I'm going to talk about, I'm going to mostly talk about a location game, which is exercise, what is that, 9.2, I think? I'm not going to try and find it really fast. 19.1. Exercise 19.1. I guess I'll just share it really quick so we can just look at it. Let me figure out this technology.
In the middle says share screen with the green button.
Okay, can you see this?
Yep.
Okay, cool. So, the way that the location game works is we've got N people who are part of like a group of citizens, and they're trying to decide if they should run for office. And the way that the example is worded is somewhat confusing. I saw a much better description in that Yale lecture Saraswati posted. So the basic idea is that if you win the election, you get a reward. There is a cost to running, which is less than the reward, which is what makes it attractive. And most importantly, or not most importantly, but also, if somebody else gets elected and their position is, oh, I'm sorry, I haven't explained a piece of the context. Let me take a step back. Oh my God. I'm just going to read this text. So we've got N people who are choosing whether or not to become a political candidate, and if so, which position to take. This is important. There's a continuum of citizens which the N people themselves fall on. They're also citizens. They each have a favorite position, so they fall somewhere along the continuum of positions, left versus right. I'm going to draw this all in a second, and it'll make more sense. The distribution of favorite positions, I believe what the book is trying to say is that it's like evenly distributed, which definitely makes the question easier to answer. So let's just say that it's evenly distributed. And so then the candidate attracts votes of the citizens whose favorite positions are closer to his position than to the position of any other candidate. So if somebody falls to the left of you and there's nobody else running to the left of you, then you get all of their votes. If K candidates choose the same position, then they receive a fraction of the votes, 1 over K. And the winner is the person who receives the most votes. And then this is the part that I accidentally jumped ahead to. Each person prefers to be the unique winning candidate than to tie for first place. By that I mean you get something, you get some sort of payoff if you win. They prefer to tie for first place than stay out of the competition. And the reason is because in the other description that I said, you flip a coin to see who wins if you tie for first place, which is like probably the same as just tying. And then they prefer to stay out of the competition than to enter and lose. So now I'm going to go to the whiteboard. Let's do that now. Okay, do you guys see this whiteboard? Okay, I'm going to assume you do. Anyway, we've got a continuum of citizens here. And let's say that they're evenly distributed along this this path. So the point that I was making when I accidentally interrupted myself was that if you, like, suppose this is your position right here, and this is the person who wins over here, winner, and you, then this distance is your unhappiness. This is like your negative value. So if it's, let's say it's K, then not only do you not get any benefit for winning, but you also get negative K for the distance between the winner and you. So that's what I was saying. And that is relevant. Oh, come on. Clear this drawing. Clear my drawing? Clear others' drawing? How do you, like, erase? Okay, whatever. Okay, so the problem specifically was asking to structure the game and show that there's a Nash equilibrium if there are 2 people running, and there is no Nash equilibrium if there are 3 people running. And this actually is a pretty close explanation of why first past the post works the way that it does and why we have a 2-party democracy here in the United States. So suppose first we'll start with like the super naive estimation. Suppose you've only got 1 person voting. Oh, sorry. Is this going to erase everything? Okay, cool. Suppose you've only got one person running, and that person runs from, really it doesn't matter, but let's say they run with the centermost position, then obviously they will win all of the votes, and they will get the payoff of being elected, and everybody else will get negative payoff for their distance from the center. But let's say that this person who's running runs from, like, oh my god, why do I want this thing? There we go. Let's say that they run from over here. Now, this is not actually a Nash equilibrium anymore, because the reason is that not everybody is in the most optimal position. You can change your strategy and get a better response, and that better response would be to, if somebody ran from over here, then they would get all of the votes to the right, and they would win. So the person who is thinking about entering and running from the center should do so. So they will get a better response. So this person over here now would have, in this situation where you've got two people running, one from the center and one from the left over here, this person on the left is actually better off not running from this position because they have to pay the money to run in the election. They don't win, so they don't get any of the payoff. And when they lose, the person who won gives them this much unhappiness. So they're actually, this is not there, but they should deviate from this strategy. And the strategy that they should do, which is where we get to the two-person Nash equilibrium, is they should also run from the center. They should run from the center, and then you get, all of a sudden, you get people clustered at the center. Now we've got J and N running exactly from the center. They both get essentially like an even proportion of the votes, and then they flip a coin. So now their payoff is going to be the expected value of flipping a coin to get the payoff minus the cost of running. So if the cost of running is if the cost of running is 1 and the payoff is 2, then basically two people running from the center create an expected value of 1 minus 1 to run. Sorry, I should definitely be writing this down. Oh my God. So if the payoff is 2, I can't write that. If the payoff is 2, is this going to work? No, you can't do text. Forget it.
There is text though.
I see it here, but it won't like let me type. I have to like draw a text box.
Yeah, it should be. Yeah, there we go.
So somebody else has got it.
Yeah, I mean, I pressed the text box and then I typed and then I pressed enter and now it's here.
Yeah, I'm not getting any such luck.
Click on the
Format?
place where you want to.
Yeah,
right?
no, I did it. Anyway, it doesn't matter. Hopefully I can just explain it well. Or maybe draw it awkwardly. I have a feeling that my mouse is just, maybe if I click over here. Yeah, forget it.
What button are you clicking?
I'm clicking with my mouse, with my left mouse clicker. Anyway. Payoff is 2. Every time I draw with the trackpad, just to sidetrack really fast, I think of Steve Jobs saying that this is like the ultimate drawing module. I'm just like, just fuck off, Steve. I feel like an idiot right now. Anyway. So anyway, the path is 2. The cost is 1. So then if two people run from the center, you're going to have the odds that they will win times the payoff, which is the expected value, minus the cost, which they will definitely incur, which is 0. So it's a wash. But it's actually, there is no better, like nobody should deviate from their strategy here, because if N doesn't deviate, then, if N deviates, then they will get the negative value of their position from the, well, basically, if I'm going to go back to the book, because I'm actually mixing examples right here, in the book example, it says that everybody would rather tie for first place than stay out of the competition. So within that context, everybody's getting their maximum value right now. And you can see right here, this is why. So anyway, that explains. So does everybody see that if there's two people running, then we're in a Nash equilibrium because nobody can deviate and get a better result? Everybody got that?
Yep.
Cool. So then the last thing to explain with this one is why 3 people is not a Nash equilibrium. So let me just erase everything really fast. So with 3 people, this should be pretty easy to, oh, we got a straight line. Of course we do. So with 3 people, so suppose 2 people are running from the exact center. Oops. And that is, you know, like, what are their names? N and J. And then X decides that, so now we've got a tie, a dead heat tie. They're going to split the votes. Now suppose that X comes in just right here. X is now going to get all of these votes. N and J are going to split all of these votes. And N, J, and X are each going to split the votes in the middle. And so X is going to win in a landslide. He's going to beat N and J by over half of each. Now, is this a Nash equilibrium? And furthermore, can we formulate one? This is obviously not a Nash equilibrium because both N and J just paid to lose an election that they knew they were going to lose. So they would actually be better off by deviating from this strategy and dropping out and letting X be the only one to run. But then, if you get into a situation where only one person is running, that's not necessarily a Nash equilibrium either, because well, yeah, that's not a Nash equilibrium either because then a second person can run, enter, and tie. So one person is not a Nash equilibrium because you have the option to tie, and 2 people is not a Nash equilibrium because, 2 people is a Nash equilibrium, but 3 people is not a Nash equilibrium because one person is best off deviating from their strategy by trying to take half of all the voters on one side, and then the other 2 people that are left in their tie are better off not competing. So do you guys see how 3 people is not a Nash equilibrium?
Yeah, but I mean, only for this case.
I know, yeah, that's what I was going to say.
Okay.
So now the last case is can we formulate one? So the book asks to prove that there is not a Nash equilibrium, but this is actually something I was somewhat confused about because if I'm not mistaken, this is fairly close to an Nash equilibrium. This is actually, no, I actually think this might be all right. So suppose you've got over here J, over here N, and then right in the dead center, X. In this case, N is going to get all these votes. J, my super awkward J, is going to get all these votes. And then these votes are going to get split between J and X. And these votes are going to get split between X and N. So we get a 3-way tie, which is good. It's better than, not running, but not as good as winning. So the question is this a Nash equilibrium? And to answer that, we have to answer the question, can anybody deviate from their strategy and profit from profit right now? I would argue that they can, because N or J can scooch a little bit closer to the center, just like 1 unit to the center. Now, N is running from here. Whoop. And that means that they get a little bit more votes than X, a little bit more votes than J. So they will win, and we will, as you can see, everybody else is going to start deviating, and then we'll wind up with 2 people in the dead center. So 3 people is not a Nash equilibrium because somebody can always, even if you get in a situation with a tie, somebody can always deviate from their strategy and win.
Awesome.
Got it? Cool. So
Awesome.
that's my stuff.
I think that pretty much all of the arguments that you made hold also in the general case where the distribution of the voters is given by a density function, which I think is what they really ask for in the exercise. Let me draw what I mean.
Okay.
I agree. You just have to place the players like dependent on the density function instead of just evenly distributed.
Yeah.
Okay. Yeah.
So like we would have, here's our line from 0 to 1. And this is like the density function of the voters. It's, I guess it's assumed to be continuous. I mean, if it's not, then there might be things that kind of get tricky. But if it's not, then like you would calculate the amount of votes that you get as an integral again. So like let's assume, without the loss of generality, that player 1 is to the left of player 2. Then the amount of votes that, and here's the middle point between them, we can formulate it in terms of P2 and P1, but I don't want to do that, so I'll just write X. I mean, the amount of votes that P1 will get is the integral of, it's actually a really bad name to call it X, because this is f of X and this is the X-axis. So did you hold down something to erase? Alt or something? Oh.
No. I just it's just the same as drawing. It is kind of buggy though.
Yeah. Oh, I should have erased that also. Anyway, let's call that point something. Let's call it. Okay, we can't call it this if you really want to. We can call it 2 minus P1 divided by 2. Is that actually correct? No. It's P1 plus this point. Okay, good. So that's why I didn't want to write it out. Let's call it B. So this would be the amount of votes given to player 1. And the integral from B to 1 would be the amount of votes for player 2. And then they would just do again, like calculate where to place themselves in order to get as many votes as possible, and that would be at the same position as player 2 if player 2 is rational. And the same thing would apply in the case of 3 players, where you would get more votes if you place yourself like an infinitesimal to the left or to the right.
Cool.
Awesome. So does anyone else have anything they want to, maybe someone who hasn't spoken, done an exercise? Or are we good with this one? I should ask that first.
I did think I'm good with this one. I did think a little bit about Bayesian Battle of the Bakar-Stravinsky, Battle of the Sexes. Thought a little bit about it. I'm kind of going to be stumbling through it if we talk about it because I'm not like well prepared or anything. But it might be worth talking about since it's part of the chapter.
Yeah.
Wait, did you call it Bayesian Battle of the Sexes?
Yeah.
Okay, which number is it?
Let me look.
Maybe you can share it on your screen.
Yeah, I will. Let me pull it up. So let's stop this screen sharing. Oop. And then let's do oh, you know what? I actually have it written. It is exercise 27.2. I will pull it up right now. Oops, I overshot it. It is right here. So, share this. You guys see that?
I don't.
No.
Now.
Oh,
No.
here we go.
Yeah. This is the same as the regular Battle of the Sexes, or Bacchus-Stravinsky. Two players wish to go out together to a concert of music by either Bach or Stravinsky. As in the original Bacchus-Stravinsky, their main concern is to go out together, but neither player knows whether the other prefers Bach to Stravinsky or the reverse. Each player's preferences are represented by the expectation of their payoff, the payoffs to pure outcomes being analogous to those given in 16.1. Model this situation as a Bayesian game and find the Nash equilibria for all possible beliefs. Show in particular that there are equilibria in which there is a positive probability that the players do not go to the same concert. So because I didn't think about it too hard, I probably won't be writing anything, but I think the basic idea is that like you've got four states, right? Like four states of nature, and those states of nature are where player one prefers Bach and player two prefers Bach. Player one prefers Stravinsky and player two prefers Bach. Player one prefers Stravinsky, player two prefers Stravinsky, and player one prefers Stravinsky and player two prefers Bach. I think I got them all. But you know, it's like symmetric or whatever. You got it. So actually, you know what? Let me just, maybe I will write. Hold on a second. So in the situation, in the original Bacchus-Stravinsky, you've got your little payoff board. Oops. You've got your lines. And then you've got, let me just draw this. B, S, B, S. So in the original Bacchus-Stravinsky, it goes like this. Do they get 0, 0 here? Or do they get, is it 0, 0? Do they get no utility if they're not together? Yeah, same thing.
Yeah, they do.
Anyway, so this is the original Battle of the Sexes. So with the four states of nature, you actually get 4 potential game boards, right? You get this one. You get the one where everything is reversed. This is going to be a lot of drawing. Hold on a second. So in this one, what is it? So in this one, player 1 prefers Bach and player 2 prefers Bach. Sorry, this one right here. Player 1 prefers Bach and player 2 prefers Bach. And this one, player 1 prefers... No, I'm sorry. In this one, player 1 prefers Bach and player 2 prefers Stravinsky. That's right. My bad. In this one, they both prefer Bach. And then, oh, wait. Oh, okay. So we're going back to 10 and 5. Okay. Let's just do that then. And this is basically, if you remember, we were calling this one Mendelssohn and Mozart, I think. So if you have this situation or the two mirrored situations, in the first game, in the situation where you prefer Bach and you don't know if the other person prefers Stravinsky, you should pick the one with the highest expected value, right? And so the highest expected value, if you prefer Bach, if you pick Bach, it will be 10 plus 0 divided by 2. Because that's the average, which gives you 5.
Why? Or what do you
Bach every time? Sorry, if you pick Bach every time and you don't know what the what your partner's picking, then
but you assume that the likelihood of them liking Bach to
Stravinsky. If you don't know, sorry, I should have been clear. If you don't know, and we assume that it's equal probability that they choose one or the other, given no information, then in that case, your expected value of choosing Bach every time is 5, and your expected value of choosing Stravinsky every time is 5 over 2. So in this case, if you don't know what your partner is picking, you should always just pick what your favorite thing is. And since there's 4 states of nature, and if there's a state of nature where you prefer something and your partner prefers something, then you will wind up with that. If it's a state of nature where you prefer something and your partner prefers something else, it is probable that you will pick the one thing and your partner will pick the other thing because you don't know what the other person's going to pick. And then then in that case, it is probable that you will not go to the same concert.
So wouldn't you choose Bach a little, like you would weight your choice for Bach a little bit more than your choice for Stravinsky, but you would still include it in your strategy? Like, I don't know the answer.
That actually gets into mixed strategy, which is the next chapter, I think. And that's where you are judging. It's like, I think that's where you like sometimes choose Bach and sometimes choose Stravinsky based on the payout, but I don't know well enough. I only like saw a little bit of it when I was researching this stuff.
I see. So we are saying we're choosing a single action.
Yep. And the main thing is that the action that you're choosing is just based on the expected value, and the expected value of your favorite one is always going to be higher than your not favorite one, all else being equal.
I am not sure that I agree.
Right. It won't always be equal because you could be in a state of nature, it won't always be, well, I don't know. What do you think, Martin?
So I think the assumption that you're making with the Bayesian probability distribution or the Bayesian reasoning of the first player should not be their estimate of what they will choose, but rather their estimate of what they prefer. So they would assign a probability that they are either in the star scenario or that they are in the circle scenario. And like, if they believe that they are in the circle scenario, they would obviously see that the best Nash equilibrium is choosing Bach, and so they would do that. Whereas if they believe that they are in the other scenario, it doesn't really matter what they choose. They might go for Bach anyway because they prefer that, but they know that both things are Nash equilibria, so they're not really sure what to do.
That's a good point. I totally mixed up. The place that you should be assigning probability, the reason that this 1/2 comes in, I think, is where you're trying to decide what state of nature you're in. So there's like a 1/2 probability that you're in the star or the circle scenario, right?
No. I mean, it would be like you would assign a probability X to the likelihood that you're in this scenario, and 1 minus X to the likelihood of being in this scenario. And then you would have the other person, they know what they prefer, but they would assign a likelihood y to being in maybe this scenario.
Hey guys, sorry to interrupt, but I have to jump out. I'm sorry I didn't do any of the assignments. I didn't realize that was, I missed last call, so I didn't know. Sorry to interrupt again, but I gotta go. If you guys do an assignment, let me know, and I'll try to join in on that.
Okay.
Sounds good.
Bye.
Yeah.
Yeah, thanks. Always a pleasure. That was really, really a joy. Thanks, guys.
Yeah.
Thank you. See you.
Yeah.
Yeah, keep going.
Yeah, so I mean, it could be the case that the actual preference of player 2 is actually to go to, what is S? Stravinsky? And so they know that, and so they are in the mirror of this scenario where it's 10, 10, oh sorry, 5, 5, 10, 10, 0 here. And they assign, okay, let's see if I can draw this. They assign probability y to them being in this scenario and 1 minus y of being in this scenario. And so in particular, if y is larger than a half and x is smaller than a half, player 1 is gonna believe that they are in this scenario. And
what was y again? What was y again?
The probability that player 2 thinks that player 1 prefers Stravinsky. So player 2 thinks that player 1 prefers Stravinsky with y probability.
Okay, yeah, that was actually something I was confused about. So both of them are, making the same reasoning. Okay, yeah, that makes sense.
Yeah, I mean, you could go even more general, I guess, and like say that they're unsure about their own opinion.
Exactly. I was like, oh my god.
But anyway, I mean, if we, well, I mean, you get my point, right? I think if they think that if player 2 thinks that they are here and player 1 thinks that they are here, then player 1 would pick B and player 2 would pick S, and they would go to a different concept.
Yeah, there you go. Yeah. That's a good point.
Because I mean, that's the formulation, right? That they are unsure about the other person's preference.
Mm-hmm. So yeah, if they both think that they're in like a Mozart Mendelssohn scenario, but they're both flipped, then it's the most probable that they will go to separate concerts.
Exactly. Yeah.
Cool. Right on. I knew that we would figure that out together because I was looking at it online, and online all of the descriptions of this are the player doesn't know if the other player actually wants to spend time with them, which is like somewhat different than this one where you just don't know what their preferences are, but you know that in general they want to spend time with you. So I was a little confused about this specific question.
Where was it exactly?
Where was it?
20.2?
It was
27.2
on page 27.
Yeah.
Yep. So that's everything that I thought about.
Cool.
It looks like it's been an hour, right?
Yep. Seems so.
You guys want to shoot the shit about crypto projects or get out of here?
I think figure out what we're doing next meeting, maybe?
That's a good point, yeah. So let's stop this screen sharing. Hold on a second. Okay, so we're back in the mix. According to the table of contents, The next information is mixed correlated. Oh, this is the next chapter. Sorry. Mixed correlated and evolutionary equilibrium. Does anybody have experience with these topics? Are they difficult or easy? I don't really know. So last time we've been doing, I don't know, what do you guys think? Should we do like 2 sections, split it in half over 2 meetings? I think that's probably good, right?
Yeah, at least I think.
We've got mixed strategy, Nash equilibrium, interpretations of mixed strategy, Nash equilibrium. That seems like a nice chunk. And then correlated equilibrium and evolutionary equilibrium. Meeting after that. Sound good?
Yeah, I mean, I'm always in favor of splitting things up into smaller chunks. So we could even split this in 3 chunks, like go for the mixed correlated and evolutionary 3.1, and then next week do 3.2, and then do 3.3.
I think you mean, well, there's 4 sections.
Oh, yeah, you're right.
I think that the first 2 look like they go together pretty closely. Mixed strategy, Nash equilibrium, and then the interpretations thereof. But I agree that we could do correlated and evolutionary each as a meeting.
On the other hand, like correlated is only 4 pages, so it might make sense to, and the other one is like 3 pages, so they don't seem very heavy.
And they do have 1 exercise each, it looks like.
Mm-hmm.
No, the second one, yeah, they have 1 exercise each.
We can just say that we're gonna start with the first half next week, and then sort of wing it from there, I guess.
Sounds good.
So the first 2 sections then, mixed and interpretations?
Yeah, so up until the headline of 3.3, right?
Yeah.
How many exercises are there? Let's look. There's 1. Looks like maybe only 1 exercise.
Yeah, but 3.
No, yeah. Oh, for sure. No, yeah. But I think that'll be good because then it'll be mostly like. Oh no, 3 in the next section above that. So yeah, 4 or 5. Oh my god. Okay, I have a feeling that maybe what'll end up happening. Let's read the first 2 sections. We might only make it to the first section and then just discuss the next section in the next meeting, but let's just read the first 2 sections. How does that sound?
Yeah,
Sounds
that's
good.
Yeah.
Do you think I definitely enjoyed doing these exercises? Do you
Hell yeah.
think it would be good to, like, you know, after a section have an exercise that maybe someone, you know, can do, or what do you think about that?
You
Like,
mean every section instead of this like chapter review thing?
I mean, I just a proposition. I don't know which one is necessarily better.
I feel like we did both in the last chapter where we went through some exercises as a group or whatever, or maybe like one person led, and then at the end we just went over some of the exercises that we couldn't get to. I think that's probably a good idea because there's like 5 in the mixed strategy section.
Cool.
Okay, cool. Awesome seeing you guys again. Take it easy. Have a good week, and see you around.
You too.
You too.
Peace
Bye,
out.
bye, y'all.
See ya.